In this video, we're going to solve a very common calculus problem. According to U.S. postal regulations, the girth plus the length of a parcel sent may not exceed 108 inches. What is the largest possible volume of a rectangular parcel with a square end that may be sent by mail? The girth is the perimeter of the smallest end. Since it's rectangular, this end is going to have the same perimeter as this end. And then we have the length here. So let's get some variables here. And we'll label this end x and this length y. Now if this is x, this is also x, this is also x, this is also x. Now, let's think about what it is we're trying to optimize. We're trying to optimize the volume. So in getting a function for volume, it's going to be length times width times height. So y times x, or x squared y. Notice it's in terms of two variables, so we'd like to have a constraint. Well, the problem tells us that the girth plus the length has to be 108 inches. So our girth is x plus x plus x plus x, so 4x, plus our length, y, that's going to be 108, as that's our constraint. Now what we're going to do is use our constraint to get our volume in terms of one variable. So I might go ahead and solve my constraint. I'm going to solve it for y. You could solve it for x just as easily, 108 minus 4x. And now we're going to use that, because this is the same y as it is here, to get our volume all in terms of x. So we have x squared times 108 minus 4x. Distributing that x squared, I'll get 108x squared minus 4x cubed. Okay? Now, we always want to be concerned about any kind of domain restrictions. Well, both x and y have to be greater than 0. So we know that x and y are both going to have to be greater than 0. If they're 0, we have no volume. Now let's think about the maximum they can be. Well, here's our constraint. So the absolute biggest y could be, that would make sense, to have x be positive. If x was 0, y would be 108. So that's going to be the absolute maximum y. Again, it gives us a volume of 0, but we know that y has to be somewhere between 0 and 108. X, very similarly, has a largest size 2. That's if y is 0. If y is 0, that means 4x equals 108, which means x has to be 1/4 of 108, or 27. So those are our constraints on our variables x and y. So now we have an extreme value theorem application, because we're now on a closed interval. So let's go ahead and find out our maximum possible volume. So we're going to go into calculus mode and find our derivative to get any critical points. So v prime, we just have a couple of power rules. It's going to be 216x minus 12x squared. And we'll factor as much as possible. So we can pull a 12x out of both terms. And that leaves us with 18 minus x. So when I set that derivative equal to 0, I've got a critical point at x equals 18. Now, let's ensure that this is in fact a maximum. It's in between our constraints, between 0 and 27. So there's 18. We're only concerned with positive values. There's another critical point at 0, so maybe we should list that, but we're not concerned about that because this makes a volume of 0. That's going to be our minimum. So to the left of 18, say if I use a test point of 17, I'll get positive times positive is positive for v prime, which means v is in fact increasing. If I use a number larger than 18, say 19, I've got a positive times a negative, so I'm going to have decreasing. So 18 is in fact going to yield the maximum possible volume. Now, let's find out what that maximum possible volume is. Well, We know that x has to be 18. And then the corresponding y, well, remember we got an equation for y here, is going to be 108 minus 4 times 18, which equals 36 for our y. So our maximum volume, so if we were asked for the dimensions, it's 18 by 18 for the girth, and then 36 for the length. And since this problem asked us for the volume, it's going to be 18 squared times 36, for which we get 11,664 cubic inches. Notice our whole problem, the 108 was in inches, so this whole problem was worked in inches, so we don't want to forget our units.